Thank you very much. Well, I'd just like to thank the organisers for inviting me to give this presentation. I've been working in this field for a few years, and it's the first time I've actually presented this work to people who are actually in the field. So I'm slightly nervous about the reaction I might get. Anyway, enough of that. This is joint work with Tom Nye, who presented this morning, and Pietro Leo, who's a colleague here in Cambridge. And it's to do with distance matrix phylogenetics, that is building phylogenies from distance matrix information. And our key point here is really this question of uncertainty. So that's what it's all about. Just a quick advertisement for distance-based methods for phylogenetic reconstruction. You can build, you can deal with much larger trees with this kind of technology. The algorithms are typically very fast, much faster surely than maximum likelihood and Bayesian methods, I think. I think for me the most important thing about this is they're less model dependent. And we had a very interesting presentation this morning from Tandy, which pointing out the difficulty in building models for example, genome scale evolutionary rearrangements. I mean, what models are we going to use, and can we believe them? And the great advantage of distance-based methods is it allows you to sweep a lot of that under the carpet. You don't really have to be explicit about what your models are. It may be that certain certain ways of calculating distances might be better if certain models are true, but you don't actually have to assume models per se. And I think so it makes these things really, I think, all of these three things really mean that distance-based methods are perhaps the method of choice for such questions. Okay, so there's been a number of methods published over the last 20 years for building phylogenies from distance matrices. Neighbor joining, BioNJ, Weber, MVR, FastME are all such methods, and all these methods are agglomerative. That is, you start off with a bunch of taxa and you sort of decide on which two you're going to join together first, and then having done that you decide which two you will join together next, and so on. And but all these methods differ, and one of the ways they differ is the way they treat uncertainty. And there's a certain level of informality about the way this is done. Let me just come to my next slide. For example, a number of methods like neighbor joining, Weber, and FastME essentially are assuming that these distances that are recorded between pairs of taxa are essentially independent, which actually is a difficult assumption to justify. The main reason for doing this is really that you can make algorithms which run fast. On the other hand, there's a number of reasons to realize that distances that you might have in your hand should be correlated. And the reasons why they might be correlated are several. One might be that they actually share evolutionary paths. So for example, between taxa A and B you have one distance, between taxa A and C you have another distance. And they're both, they should be correlated because they share this little path here, and so sort of variations in that path length will affect both distances. So they surely should be correlated for this reason. And this has been recognized for a very long time by Chakraborty. I think was one of the first places where this was noted. So this is a very old observation. And some more recent methods have tried to incorporate this. But there's other reasons. For example, if your data originally come from sequence comparison, so you've done a multiple alignment, you've looked at distances between pairs of taxa based on their sequences, then they should be correlated again, because if you've got a sequence here, then it's going to affect both the distance from A to B and the distance from A to C. So any sort of variations or noise in that distance, or the fact that you haven't seen the whole genome, you've just looked at a short sequence, it's just an estimate of what's going on, they'll be correlated. Any distances coming will be correlated. And we also show, and I don't think this has really been made explicit in the literature before, there's another reason to expect distances to be correlated, and that is as you're going through this agglomerative process, that every time you do that, you're estimating something. Every time you join two taxa together, you're estimating something, And the process of estimation inevitably means that the distance matrix you have in your hand that you're working with at any point in this agglomerative process, correlations will be induced whether you like it or not. So you might even start out with independent distances, but they won't remain independent for very long. They'll all become horribly correlated because of the process that you're going through of agglomeration. There's no way to avoid that. And so this is another reason why you have correlated distances. And if you have correlated distances, you can't use ordinary least squares or weighted least squares types of methods. You may use generalized least squares, and such methods of these have done that, although apart from this one, these are not agglomerative. So this is what we're doing. We've got two types of tree that have been looked at in the literature. These ultrametric time tree, what I call a time tree, is ultrametric. We're measuring time down here, time of millions of years ago. Here are our current taxa, and this is the sort of species, the taxon tree that perhaps underlies the data. Now, that's a sort of what I call a time tree. There's also a divergence tree where the branches here, the length of the branch depends on how much evolution has happened. So, for example, on this branch, we imagine there's been more evolution taking place for one reason or another than on a branch like over here, for example. So these things get distorted. And this is what we call a divergence tree. It's non-ultrametric because the tips of these branches don't line up. So that's what we call divergence. Now I want to make a key distinction between divergence and distance. In our language, the two are different things. And what we mean by divergence is true distance. You know, if we were able to somehow see the truth, this is what we would see. We would see the true distance that is uncluttered by noise and other effects. It's actually the integrated rate of evolution along a branch. And of course, we can't ever see that unless we're actually watching evolution take place in front of our eyes. So we never actually see divergences. We only ever see distances, which are measurements of them. And so another term that's used here is path length. So I hope you understand the difference between divergence and distance. Divergence in our language means the truth. That distance is just something that you've measured or estimate. You're trying to estimate a divergence, and that is a distance. So which is the right kind of tree to assume? Should we be thinking of a time tree, ultrametric time tree, or should we be thinking about a divergence tree? The ultrametric tree appears to make stronger assumptions. And certainly in the literature there are different methods for estimating these two types of tree. But of course it's obvious that both trees are actually correct. They're just different things. They're measuring different things. They're slightly different processes. They have the same topology for sure, but they have different branch lengths, and both are correct. One is in terms of time, one's in terms of divergence. So that's a key point. And our method actually coherently integrates both types. Rather than trying to say, have we got an ultrametric tree or have we not, we say we have both. Both are correct. And we have to try and build a connection between these two things. So our method coherently integrates both types, as you'll see. And it produces a rooted tree, and it doesn't require any outgroup to do this. So this is an agglomerative stage of the agglomeration process that we go through. We imagine that we started off here, for example, with 6 taxa, and we've already started this agglomerative process. And over here, we've already joined these 2 taxa to make this one I've called A. We've already joined these 2 to make this one called C. And in this particular simple illustration, I've just got 4 taxa which remain. I've got this ancestral one here, B, C, and D. So of course we can deal with more taxa, but this is just for illustration. So that's the time tree. We have 4 taxa on the time tree, and we imagine we've already estimated the time at which this ancestor lived, and likewise here. And this is our corresponding divergence tree. We've estimated these divergences already here, and the rest we don't yet see. We can see these 4 species, and we're thinking at this moment in time, we're thinking, should we be making an ancestor here, which we will call E, which is the ancestor of these 2 taxa. Of course, the way I've drawn the tree here, that's the right answer, but we don't yet know which is the right 2 taxa to agglomerate next. But that is, we're playing around with the idea, should we join these two species together next? So that's the question. Should we do that? And we don't see the rest of this tree yet. That's all hidden from us. So the only bit we're interested in, this bit we've already done, and this bit we haven't yet done. We're just asking the question, is this bit right? And if it is right, how long should those branches be? So, am I doing for time, Catherine? 10 minutes, good. Is that 10 minutes till the questions start? Done. Oh, I should get through about half of this, never mind. So this is an obvious truth, that the divergences are additive. So if we look at the, these D's are, this is the distance between, sorry, the divergence between taxa A and B here. And you can see it's made up of, oh, I didn't need to do that. It's made up of two pieces. Oh, this doesn't quite work the way I expected. All my animations are not going to work, never mind. So it's made up of two pieces, this bit here and this bit here. And it's simply additive, that has to be the case. And we've also got these relations here. For any x, any node x, which might be C or D or anything else, we have this relation too, that the distance between A and, let's see, say C, sorry, the divergence between A and C has to be the sum of that little branch there and the rest of it going around here. So we have these divergence relationships which form the sort of basis of our model. But the things we observe, the things we estimate are not divergences, they're what I call distances. They're only imperfect measurements of a divergence. So we've actually got a situation like this. This little thing with a hat on is the thing I denote a distance with. So a distance that we might see between A and B is actually measures the underlying divergence, which is the sum of those two components, and there's a little sort of bit of noise on the end, an epsilon, a little bit of, hopefully a little bit of noise on the end. And for each of these other nodes, we can write down similar relationships. So these are, on the left, these are all distances, and these are all divergences. And this basically starts to look now like a statistical model, because we've got something on the left-hand side, which are, if you like, our independent variable. We've got these things in the middle, which are parameters, and we've got some errors. And in fact, you can set, this is really just, it's very straightforwardly a regression model. And that's the way we deal with it. Oh, it does work. So those are divergences. These are the parameters of the regression model. Here our errors are, we'll assume them to have a zero mean, so that our distances are unbiased estimates of the divergences. And we can build a regression model, and these are the model parameters. Okay, now what about divergences? How are divergences related to time? This is the other part of our model. This is not an alternative model. This is an integral part of our model, and it's essentially what makes this this approach rather unique, because we're actually trying to correlate divergences with underlying time. So we're trying to make the connection between the time tree and the divergence tree, and this is the way we do it. On the left here are the divergences. These are not distances. This is the underlying true divergences, and it's related to time. This will work, yes. So these are the divergences. No hats on them. They're divergences. And these are, this TE is the time of this ancestor that we're trying to impute. So this is the time of this guy here. That's when he lived. And this is a parameter of this model. And these are some errors on this relationship, which is to do with the distortion, the way that divergences are not exactly the same thing as time intervals. And again, we'll assume that these have zero mean, and we'll also assume that they're uncorrelated. In other words, the sort of stretchiness in this branch is independent of the amount that this is stretched or shrunk is independent of the amount that this branch is stretched or shrunk. And I notice that I call these deltas. So I'm just asking you to remember a little bit of notation. The epsilons are the differences between divergence and distance, and the deltas are the difference between time and divergence. So we've got two kinds of errors, and this is what is known as a random effects model. So we've got two things going on. We've got one part of the model I showed you previously. This is another part of the same model. Two things going on. Together it's called a random effects model, or otherwise known as a hierarchical model. But I've only told you so much about the means. I've said all these epsilons and deltas are zero mean, but we have to say something about the variances and covariances. So this is the key point of the model, and that is that we're going to assume that the variance of these epsilons has this rather strange structure here. And let me tell you what's in here. We've got a parameter which controls the amount of noise. We've got a thing there which is the size of the clade that A sits upon. So if A is a tip of the tree, then N is just 1. If this was some other thing like in an interior node, then it would be more than 1. And we have two other terms here. And these V's have a rather complicated functional form, which I'm not presenting to you. I mean, we've worked out what the form is. But this depends very much on the structure of the clade. So it might even, this V might even be 0 if we're looking at the tip of a branch. So what else have we got here? We've got a covariant structure that we assume here between the two epsilons. This is the epsilon that relates to the branch going from A to E. This is the branch from A to X, some other node X. And notice that we only have a term here for the shared node. So node A is shared between these two. We have a term here. It's exactly the same term as that. It's an identical thing here. But if this was a B here instead of an A, for example, this would be 0 because they would have no node in common. So we're assuming that. And then there's one other thing which is quite important. This is the part of the model, the random effects part of the model. We're assuming that these deltas actually are proportional to the elapsed time. So variance is proportional to elapsed time. This is quite a common thing that's been discussed in the literature. So it goes way back to Chakraborty and others, but more recently been used by these authors. It's a natural thing, and I think it's kind of inevitable that you come to that kind of conclusion. If not proportionality, some other functional form may be exponential. And we can deal with that too. I've just done it here simply for simplicity's sake, assume it's linear. And this thing here, it controls distortion. Sorry, this is the amount of stretchiness in a branch that relates the time tree to the divergence tree. So those are our variance assumptions. And these are constants, yes. These, indeed they are. Hopefully, yes. So these two things here, sigma squared and nu, are constants that are constant across the whole tree, across the whole estimation process. And we have to try and estimate them as we go, and we have methods for doing that. And these are our variance parameters. We have to estimate those. So a few words about the estimation. The time tree and the divergence tree are estimated simultaneously by generalized least squares. What do we do? How do we decide which two taxa to agglomerate at any given stage? It's very simple and very natural. We evaluate all the possible agglomerations at a given stage, and we simply choose the one which would have happened most recently. So it's just based on time. It's not we don't choose which two things to agglomerate according to some complicated and sort of variance thinking. We're just saying, well, which one would have happened next as we go back in time? Unless we choose that one. So it's perfectly natural. I don't think other methods do this at all. The beauty of this method is that these estimated divergences, that we're estimating divergences, they're the parameters of our model. They actually become the distances for the next stage. As I said before, a distance in our terminology is an estimated divergence. Well, each stage we're estimating them, so they become the distances for the next stage of the algorithm. Oh, 1 minute left. Okay. And so that variance formula which I gave you is actually closed. In other words, as you go through this agglomerative process, the variances stay within that complicated variance form that I gave you on an earlier slide. And that's the real strength of this method, that we worked all that out. And that is the surprising kind of variance form that is dictated by the algorithm. So you might have been wondering where those things come from, and that is in fact where it comes from. Another thing is it has same time complexity as BioNJ. We've done a huge amount of work to try and get the computations down. We can do this exactly, and it's no different to BioNJ in terms of time complexity. And the method's called StatTree, and here's some simulations which I'll leave there. I won't go through them, but all this is really saying is that our method outperforms BioNJ on the simulations that we've done so far. And I'll stop there because I want to leave time for at least one question. Thank you.
Any questions?
Yes, two. The first is your model can lead to topology, to phylogenies that has negative branch length.
Could
and
do.
the second is how your model perform in terms of consistency with the other model, for example, GLS. We know that, for example, weighted LS or GLS, they are inconsistent. Or, well, there are some specific particular cases in which VLS is consistent, but in general, they are not, they are inconsistent. So how do your model perform?
I think the answer is that certainly negative branch lengths are possible. Negative, but it's unlikely to happen. And where we've managed to sort of make it happen through simulations, it's not really sort of, it kind of may make a join wrong, but then it'll recover. So it's fairly robust to such things. It's not actually a big issue. The question of consistency we haven't really looked at, and I don't know the literature on this, I have to confess. But I think in terms of, if one imagines that sequence lengths are getting longer and longer, I think like most of these methods it will be consistent if that's the thing we're allowing to run to the limit. But I wouldn't want to stake my life on that, but I think that's the case.
Yeah, I just wonder, about 20 years ago I met people from Dortmund in the statistics department there. I don't remember the name, but I can find out later, who sort of started to analyze phylogenetic data with a very similar approach. Just saying, okay, it is the true thing plus some error type, and we make statistical assumptions about the error.
Okay.
Did you ever see this?
I don't know I don't know who these people would be, but I've maybe not seen that.
I will.
Yeah.
That's 20 years ago.
Yeah.
Of course, from modern point of view of science, it should be forgotten.
Probably not.
I don't think so. Maybe we can defer any questions for Wally for the coffee break and we move on.
Okay.